Okay, so again, let me start off by reminding you what the course is about. One of our big concerns as humankind is, as humanity is, global warming. That's one of the biggest problems. And how do you mitigate? How do you address that problem? I'm sorry. Reducing your carbon footprint. Okay. So what this chapter is about is okay. So here's the global carbon footprint. Okay, the transportation industry has a quarter of a global footprint, carbon footprint. Okay, the construction industry about 40%. Okay, and you can see this that the operational building operations is almost 30%. This is the air conditioning and heating and stuff like that. Okay, so again, by the way, next Tuesday, a week from today, there's a professor from University of Rome coming and talking about what is being done for this issue. Okay? This is the issue we're going to talk about, and where is the carbon footprint coming from? The flight industry, the shipping, personal transport, railways, and stuff like that. Okay, reducing the carbon footprint of the flight industry will be a tough one. Okay, today we'll talk about cars. Okay, so that's what this thing is about. Okay, all right. I will. You guys can read all of that. Okay, so I was changing slides just a minute ago, and that slide became extra. Anyway, all right, so here's the history of battery electric vehicles. Okay, the first one was built in 1830. Okay, I didn't know about this till I started teaching this course, I guess. They became practical around 1880s, and from 1880s to 1920s, the battery electric vehicles ruled. So they were more popular. So 40 years. Bees were more popular than gasoline vehicles till then because they were cleaner, quieter, more reliable, easier to start, had more power. Okay, so you could go 0 to 60 faster than them if you could go to 60. Okay. What did they lack? Range. And that's what, so the gasoline vehicles had range. So once you fix all these in the gasoline engine, then the gasoline engines would take over. Okay. Go ahead. All right, you look like you were going to. All right. So, so by 1930, the gasoline engines fixed all those problems, beat out BEVs. The reason for growth, vehicle had longer range. That was the main thing that tipped the scale in their favor over electric vehicles. Invention of the electric starter made them easier to start. Okay, mass production techniques made them less expensive, and their reliability improved. Okay. So again, range is when they beat up. Okay, and that's what even today we are fighting for the electric vehicles. You want to make sure that they have enough range. So a longer range battery. A battery electric vehicle is just essentially a battery with wheels. The bigger the battery, the larger the range. Okay. And then the question is, so when you buy a gas car, you're not worried about, there's a gas station everywhere. Is there a charging station everywhere? That's the question, okay? The question is, can you drive across the country and find a charger, okay? So, but soon there'll be chargers and coffee everywhere, so that won't be an issue. All right. So in the 1970s, with the oil prices spiking, there was renewed interest in battery electric vehicles. So the first one was produced mass produced was by General Motors in the late 90s. Okay. And then apparently Toyota had a RAV4, which was an electric version of that. I don't know if you guys, anybody remember the RAV model. Yeah, you're too young for that. So, but um, anyway, so they both use nickel metal hydride batteries. Okay? And we'll talk about batteries. We'll talk about how lithium ion batteries work. Okay? So for transportation, the idea is the following, you got to carry your energy. Okay? So in a gas car, it's the gas tank that's carrying your energy. In your electric vehicle, it's the battery that's carrying energy. Okay? So what is it that you want? You want your batteries to pack as much energy as possible and to be, what else would you like for your battery to be?
Lightweight.
Oh, very good. So you want high energy density, carry more energy per pound, and and be lightweight. Okay. So the range will determine how much energy you pack in, and if you want to transport okay, this is not my weight, but we'll make it easy. If I want to transport a 200-pound me, it doesn't make sense to put me in a 10,000-pound vehicle to transport me. That's wasting a lot of energy. We talked about this. Okay, so in a battery, you want high energy density is what you want. Okay, so we'll talk about that. All right, here's what the future looks like. So this is a projection. So in about 15 years, okay, so the global personal vehicle sales will be about 110 million, and 60 million of those would be electric vehicles. That's the projection. And the more electric vehicles there are, if your electricity is coming from solar panels and wind farms, then what is your operational carbon footprint? Nothing. A big fat zero. Okay, and that's what we're about. Yeah. All right. So transportation requires portable energy source. Okay. Gasoline is an ideal fluid because it packs per pound. It packs the most energy. Okay. And not only that, it can release the energy fast. You just burn it, and the heat can be transported to your wheels fast. The problem is it has a carbon footprint. Okay. So we'll look at electric vehicles powered by renewable electricity will have zero operational carbon footprint. Okay. And that's what we like. Okay. Okay, so here is something called a Ragone plot, and you want to understand this. Okay. And see, the idea behind this plot is, it's in one graph, you're putting so many different technologies. And this is what is called a log plot. And what it does is specific energy. This is energy, watt hour, energy per kg. So energy, a kg is 2.2 pounds. So you can think of it as energy packed per pound, and specific power, watts per kg. Okay, again, how fast can you release the energy? Okay. So for instance, if I put gasoline in my car, and to extract the energy from the gasoline, if it takes several hours, that's not a good source of energy for transportation. Okay, so what you want is to be able to pound more energy per pound and to be able to release it fast. Okay, so that's what you're looking for. Okay, so 10 to the power minus 2 means 0.01, 0.1, 1, 10, 100, 1,000. So each of these notches are growing by a factor of 10. Okay, this is 10, 100, 1,000, 10,000. Okay, so the nice thing about this graph is, see, capacitors, this is how much energy they carry per pound. Gasoline carries 10,000 times more energy per pound. Okay, that's why your cars are not run on capacitors, because you can't pack enough energy. Okay? We'll come to capacitors later in the chapter, but so this graph, you can see that it allows you to put very diverse technologies on one graph. Okay. On this graph also, what these lines say is how fast. Okay, so the energy contained in a kg of gasoline can be released in a tenth of an hour, in 6 minutes. Okay, that's what it says. How fast can you release the energy? Okay. Fuel cells, we'll talk about them in the next chapter, and they release their energy a little slower. Okay. So a point in a Ragone plot represents a particular device or technology. So here are the existing technologies. So maybe you could come up with a new technology there. Okay. What are you looking for? You're looking to replace the gasoline engine. So you want to come up with the technology somewhere there. Okay. Right now, lithium-ion batteries, those are the best technologies, okay, that you're going to release. I mean, you have right now. So what you want to be able to do is move a little more in that direction to completely beat them up. Okay. So, I mean, lithium-ion is not going to beat. Maybe you can come up with a better technology somewhere there. Okay. And all right, so that's what this is. Okay. So a Ragone plot is used for comparing various energy storing devices. Okay. On such a chart, the value of specific energy are plotted versus specific power. Both axes are logarithmic, which allow for comparing performance of very different devices. Okay. Okay, so I want to point something out. Okay, these lines are called isocurves. They're constant operating times in a Ragone plot. Okay, so along these plots, so if you had a technology here, that technology could release per pound of its energy in 36 seconds. That's what this means. Any technology on this line. Any technology on this line is releasing the energy content of its per pound in 6 minutes. Okay, that's what those means. But anyway, so these are isocurves. All right, so again, something near the bottom, what this is a technology that can release its power very fast, but it doesn't have too much energy. Okay. Here is a technology that has a lot of energy per pound, but it cannot release its energy fast. Okay. You want to be on the right corner. You want a lot of energy per pound packed in, and to be able to release it fast. Okay. So that's where you want to build your house. Okay. So devices at the bottom right corner of the plot do not carry much energy, but can deliver the energy fast. Sources on the top left have high energy densities, but cannot deliver the energy fast. Okay. So, all right. So for instance, fuel cells. So fuel cells you'll learn about this, and we'll use hydrogen. So let me give you an example. When you get in your car, you want your car to accelerate fast. You want to go from 0 to 60 fairly fast. But let's say you're using a train to transport stuff. Do you care about the train going from 0 to 60 fast? No. Okay. So there, a fuel cell where acceleration is not important, you can use those. Okay. So the Ragone plot shows that the internal combustion engine running on gasoline have the best combination of specific energy and power. So the gasoline engines have the best combination of specific energy and specific power. Okay. Energy per pound and power per pound. All right, so for transportation, you got to carry your own energy, and the battery electric vehicles are going to carry energy in batteries, of course. Okay. So batteries, we're going to talk about this chapter. Hydrogen, which will be used in fuel cells, we'll talk about in the next chapters. Okay. Primary batteries are non-rechargeable. Okay, secondary batteries are rechargeable. So that's, of course, so you're going to use secondary batteries in your electric vehicles. The Tesla battery, by the way, if you go look at it, it can be recharged about 1,500 times. Okay. And each charge, if it gives you 300 miles, 1,000 times 300 is 300,000 miles. Okay. So the battery lasts between 300,000 to 500,000 miles. That's the claim. Okay. And that's pretty good. I'm driving a car that's a gasoline car that's got 250,000 miles on it right now. Okay. I bought the car new, and so cars last rough. Gasoline cars also roughly last that long. Okay. So the lithium-ion battery shown can be recharged between 3 to 5,000 times. Okay. The range of the battery electric vehicle depends on the total energy stored in the battery. So all the different models, Tesla models, the prices are really essentially based on the size of the battery. Okay. All right, so here's how lithium-ion batteries work. Okay, so maybe you want to pay close attention to this. So this is the sort of essentially the best information in this chapter. Okay. So here's a lithium-ion battery. Okay. So for a battery, to build a battery, what you need is to build a battery, you need something that gives up an electron easily. Okay. And then you want something else that wants an electron bad. So those are the two main ingredients of a battery. Okay. And then you want the mediator and stuff like that. Okay, so to make a battery, you want something that gives up an electron easily and something else that wants it worse. Okay. This is a graphite matrix, the hexagonal structures. Those are graphite matrix. That's graphite. Graphite is the lead in your pencil. Okay. Now this guy will give up his electron easily. Okay. And the green circles, those are a lithium metal oxide. Right now, I believe it's lithium cobalt oxides that are being used. Okay. And that guy wants electrons bad. Okay. So if an electron moved from a graphite to a cobalt, it would release energy. Okay. So here's the deal. So the graphite, you talk the graphite out of giving it an electron, then that electron goes out, it runs your car, and then it comes back here and it goes to this lithium metal cobalt. Okay. So did you guys understand that? The graphite wants to give up its electrons easily. This electron, you grab this electron, send it through the car, through the electric motor. It does its job, and then the electron goes to the cobalt, lithium metal oxide. All right, well, why is it called a lithium-ion battery? Okay, so when the graphite gives up its electron, it's become positively charged. Okay, and lithium atoms give up their electrons even more easily. So they give up their electrons to the graphite, becomes neutral. Lithium now has become positively charged. And this positively charged lithium ion goes from, is transported through the battery, through a separator. It goes here, and that electron that came over from here, which was absorbed by the lithium metal oxide, that neutralizes the lithium ion. Okay. So, in essence, what we did was the graphite gave up the electron to something that wanted the electron even worse. Okay. So the electron essentially fell from a higher energy level to a lower energy level, and that energy was used to run your car. Okay. So that's the discharging of the battery. So again, for any battery, okay, whatever technology it is, okay, so these two are the basic ingredients in a battery: something that gives up an electron easily, and something else that wants the electron worse. Okay. All right, I'll pause a second and see if you guys have any questions. Okay. So, all right, so when a battery is connected to a device, electrons from graphite in the anode will travel through an external circuit toward the lithium cobalt oxide in the cathode. Okay. The stored lithium atoms in the anode now give up one of their electrons to the carbon, become positively charged lithium ions, and travel through the electrolyte to the cathode. They travel through the battery to the cathode, where they gain the electron back, arriving from the external circuit. Okay. So a fully charged battery will have all the lithium ions here. All the red dots will be here. A fully discharged battery will have all the lithium ions here. Okay. So when you recharge the battery, what you're doing is you're grabbing electron from these guys, the lithium metal cobalt, taking the electrons and bringing them back there. These guys don't want to give up their electrons, so you have to spend energy to rip that electron off, okay, and bring it here. So when you take the electron off, the lithium ion will give its electron to it. The positive ion will move over there and charge that electron. Okay. So when you're charging the battery, you're moving all these electrons back there, and you have to spend energy to do that. Okay. Did you guys understand that? Okay. All right. So when the battery is charging, the opposite process occurs. So when a battery is charged, what have we done? Electrical energy is stored as chemical energy in the battery. So when you charge the battery, you're putting in electrical energy and storing it as chemical energy in the form that lithium ion is moved over there. Okay? And that chemical energy gets when the battery discharged, you lose that chemical energy, stored chemical energy. Okay? So in the case of lithium-ion battery, when the battery is charged, all the lithium ions atoms are on the anode end. When the battery is discharged, all the lithium atoms are on the cathode end. Okay, so when it's charged, all the red dots are here. When it's discharged, all the red dots are here. All right, so if you guys understood that, I'm happy. Today was a successful day. So I'll pause again for a second. And if you have any questions, I'll let you guys ask them. All right. So secondary battery properties. So we are interested in secondary batteries. These are, so here's lead acid battery, nickel cadmium, nickel metal hydride, and lithium ion batteries. Okay. So Again, in your car, what is it that you want? You want the most energy stored per pound, and you want the battery to release it fast. Okay, so this is specific energy is how much energy is stored per pound. Specific power is how fast it will release the energy. Okay, so we want these two numbers to be high. That's what we're looking for. Okay, so specific energy. Okay, you see that lithium ion beats out every other technology by a mile. Okay. Specific power, see the nickel metal hydride, that has the highest specific power. Okay. Lead acid batteries, the specific energy is, this is megajoules per kg, is 0.13, and it has a specific power 1/3 that of lithium ion battery. Okay. Do you guys know anywhere where you use lead acid batteries? Where do you use them? Golf carts use them. Okay. So those are heavy and they don't go fast. Yeah. Okay. Well, all right. Well, I said they don't go fast, and so they can. Huh? Well, I mean, you certainly wouldn't drive them on the highway. Yeah. So, all right. And life cycles. So lithium-ion battery has a life cycle of about 1,500 recharges. Okay. So okay, so right now the lithium-ion battery can be recharged 1,500 times. Let's say you come up with a lithium-ion battery that can be recharged 5,000 times. What did you effectively do?
Made a better battery.
Okay, can you tell me in economic terms what does it? You reduce the price by 1/3 to 1/3. You increase the lifetime of something 3 times, you're reducing the price to 1/3. Okay? So, and this is the kind of stuff that goes on. For instance, if you have a solar panel, you're selling a solar panel of 20% efficiency, and she's selling a solar panel of 25% efficiency. What did you do? You reduced the amount of land needed by 20%. You know, that's the kind of stuff. Okay, that's the kind of calculations that go on in things. Okay. All right. So here are lithium-ion batteries. Their prices have been decreasing tremendously. Okay. So this is dollar per kilowatt hour. That's a unit of energy. Okay. So how much does it cost to pack that much energy? Okay. So this was $1,000 then. In 10 years, you can see that it's reduced by a factor of 10. And do you guys see the effect of this? Yes, now they can sell you lithium-ion batteries, weed whackers, lawnmowers. It's showing up everywhere. E-bikes, all because of this. Okay. So you're not going to sell an e-bike at that price. Okay. And now you can buy an e-bike with a 50-mile range for $500 or whatever. Okay. All right. So so what we're going to show here is the following. Okay, what is it that you care about your car? You want to be able to drive, I mean, if you had to recharge your electric vehicle every 100 miles and then it took 30 minutes to charge, you're probably not going to buy it. Okay. So let's say we'll let you drive about 300 miles, 350 miles. How much will the battery pack weigh is the question. Okay, that's what this calculation shows. So 600 kilometers is about 370 miles. Okay, I'll tell you precisely how much. Okay, 375 miles. That's 375 miles. Okay. Okay, so for a 375-mile range, okay, what the calculation is, the lithium-ion battery, the weight of the battery is 1,600 pounds. Okay. If you check your car, most of your cars are about 2,500, 3,000 pounds. Okay. Half the weight is in the battery. Okay. For that kind of range. Okay. So what this number says is, so the a gasoline car is 17% efficient. The energy content for every kilometer you drive, you've used up this much gasoline, that's the energy content. And with 17% efficiency, that's the energy delivered to the wheels per kilometer. That's what these numbers are saying. A battery-powered car is 90% efficient. If you're wasting energy on a lot of the foo-foo stuff, that's where the efficiency comes down. Okay, so if you want this much energy delivered to the wheel, this is how much energy you want from the battery per kilometer. Okay, and what this number shows you is for a 375-mile range, this is the specific energy of the battery, of lithium-ion battery. This is that number. This is that number. Okay. Again, you don't have to know all of this. So all this is saying is for a 375-mile range, the battery weighs about 1,600 pounds. That's what this is saying. This calculation is showing it. Okay. And with that battery power, you have a 290 horsepower car. Yeah. So you have a pretty powerful car. Yeah. Okay, so for the battery vehicles, these are the issues that you're trying to solve. Range, again, and initial cost. Okay. Right now, battery vehicles are about 2 times as expensive as gasoline cars. Okay. Replacement costs, okay, and recharge times. Okay, how fast can you pump gas? In about 3-4 minutes. To recharge the Tesla takes about, even at the fast charges, takes about 30 minutes. Okay? And this is the main concern, more than the recharge time, the recharge infrastructure. Okay. And so you want a nationwide network of recharging station. Does anybody own a Tesla here or an electric vehicle?
My doctor does.
Mm-hmm.
He's got a charger at the office.
Have you driven it? Have you driven in?
I've ridden in it.
Mm-hmm.
We rented one.
I'm sorry?
We rented one.
Oh, yeah?
We drove to Tampa.
Door to Tampa?
It didn't stop.
Where did you rent it from?
Turo.
I'm sorry?
Turo. It's like Airbnb but for cars.
Oh, I see.
Mm-hmm.
Yeah. And here in Daytona,
Mm-hmm.
what did you think of it?
Nice.
Mm. Yep. How many of you would buy a Tesla or an electric vehicle if you? Yeah.
There are these guys on Shark Tank that,
I'm sorry?
I saw this pitch on Shark Tank and these guys are coming out with, a portable unit that you
Mhm.
can keep in your car to be able to take it with you to recharge whenever you need it.
Like a roof.
Now, what does that? So it's just like for smartphones and stuff like that?
No, for your car.
Yeah, I know. So the
Like a portable charger.
portable charger, and except for your car. Yeah. Well, again, you're adding weight to the car.
Yeah, right now it was too big, so
Mm.
they said they're working on a smaller unit so
Mhm.
you can put it in your car.
I see. Yeah. Well, they're also doing another solution where, and for two-wheelers and stuff like that, Instead of recharging, you just swap out battery packs and stuff like that. You, you go, and that's a much faster solution. Anyway, yeah. I think recharging time is not that big an issue. Recharging infrastructure and cost, and if you can,
How long does it take to fully charge a car?
at the fast charging stations, I believe 30 minutes. But slow charges are 3 to 4 hours at your house. But they're fun to drive. I've driven a friend's car a while ago. They're really fun to drive. Okay, so the gasoline cars are, what this number shows you is the gasoline cars are 20% efficient, okay? Even if the electricity came from a carbon plant, from a coal-fired plant, their carbon footprint is half of that of the gasoline car, okay? So even if the electricity came from a coal power plant, you can say the efficiency has gone down to 35%. So this is essentially a proxy for the carbon footprint. Okay, so for the ICE, the carbon footprint is 20%, and for the electric vehicle, it's 35% if the electricity is coming from a coal plant. But if the electricity is coming from solar panels and wind farms, then the carbon footprint is 0. Okay. All right. So now we'll talk about other stuff. Okay. So here are capacitors. What are capacitors good for? Okay. Storing energy. You can't store much energy. See, you store energy about 10,000 times less than in a gasoline per pound. But these guys can release it very fast. Okay, so what you can do is you can use capacitors, and some electric cars do this. So when you brake your Tesla, okay, when you brake a gasoline car, what happens to the energy of your motion?
It's not,
I'm sorry?
it's not. Friction.
Turns into heat, and it's just thrown away into the environment. All these electric vehicles, when you brake the car, that energy is used to recharge a battery. So it's not wasted. Okay? And what you can do is you can recharge a capacitor, and the capacitor can release it fast. Okay, so a lot of electric cars do that. Or there are technologies that do that. Okay? So what does that do? Increases your mileage. Okay, so city driving, your charge lasts better for city driving than for highway driving, because you're reusing that energy all the time. Okay, so capacitors cannot store much energy, but they last a long time. Okay, so here is a small capacitor. This is 3,000 farad. 20 years ago, 1 farad capacitor is a large capacitor. So we have a very old, 30-year-old 1 farad capacitor, which is about that big. Okay, so now they can make large capacitors very small. Okay, so capacitors can store electrical energy in an electric field by separating positive and negative charges. Okay, so let me show you what I Anybody see a capacitor? There.
Yeah.
Okay, so here in this thing, a capacitor is 2 metal plates. Here's a battery. Okay, so what is a battery? Huh? Yeah, it stores energy. So when you pay money, what you're doing is paying for energy in this form. Okay. Now let's see. So the battery will, and now we'll connect the battery. Okay. So what happened? Electrons flowed from here to there, and and then these electrons repelled electrons from here, and this became positively charged. So in effect, what did you do? You took energy from the battery and transferred some of the energy from here to there, to the capacitor. Okay, why did you do this? Okay, the reason was, from a capacitor, you can release the energy very fast. This is what happens in your flash camera in your cameras, the flash bulb in your cameras. When you take a flash picture and your camera is blinking that yellow light, what is happening is the energy is being transferred from the battery of the camera to the capacitor. And then when you take a flash picture, the energy from the capacitor is released into the flash bulb. Okay, so a capacitor can release the energy very fast. Okay, and that's the we have that here. So flash. Okay, so we're going to oops. So we've charged it and then release it very fast through the flash bulb. Okay, so there is your flash camera circuit. All right, supercapacitors or ultracapacitors store more energy than traditional capacitors. Okay, they can be used to run public transport buses in cities. Okay, so here is the So here is the deal with these buses. They use supercapacitors. The problem is the capacitors cannot store energy too much energy. But public transport it's great for that. You go to the next stop, recharge. By the time people get in and out, you can recharge. So these capacitors can be charged in 10, 15 seconds. And then you go to the next stop, recharge. Okay. So China has a lot of these buses, and this is good because in big cities, if you use a gasoline car, a bus, it creates smog and pollution. This thing can clean up air. Okay. So supercapacitors don't hold much energy as batteries, but they last for years and charge quickly. Okay, so they're perfect for mass transit system with frequent stops. Some models can charge in 10 seconds. They also consume 30 to 50% less energy than other electric vehicles. Okay, because you can use the regenerative braking thing. Okay. And another thing is they can be recharged millions of times. Capacitors can be recharged millions of times. How many times can the lithium-ion battery be recharged? 1,500. Very good. Okay. All right, so here are some formula regarding capacitors. You don't have to worry about this. The capacitance depends on the area of the plate divided by the distance between the plate. And this is a number related to vacuum, and that's a number related to stuff that you fill it with. Okay, so that number increases the capacitance. Okay, the energy stored in a capacitance is the capacitance times the voltage you've charged it to square. Okay, so again, you don't have to worry about all these formulas. Okay, so you want to store as much energy as possible, and the higher the voltage you can charge it to, the more energy you're storing. Okay, so the question is, what is the maximum voltage you can charge it to? The maximum voltage depends on, you don't want sparks flying between these two plates and discharging it. So that's what determines the maximum voltage you can charge it to. Okay. So supercapacitors maximize energy density. What does that mean? They pack more energy per pound. Okay, so that's supercapacitors are just large capacitors. Okay, so supercapacitors, here's the thing. Up to 1 million charge-discharge cycles. Okay. What is the ding against them? They can't store too much energy. But so these are perfect for mass transit systems. Where you use so high power density. High power density means you can withdraw the energy very fast. When you can withdraw the energy very fast, what does that also mean? You can charge it very fast. So you saw that in the public transport system. You can charge it in just 10 seconds. It's discharged, and by the time people get in and out, you've already charged it again. Okay. Yeah. So fast charge is discharged. No sophisticated charge electronics needed, so that is cheap as well. Okay. So some applications for supercapacitors include auxiliary power for battery electric vehicles when there is demand for more power. So what that means is some electric vehicles, what they do is, so you're coming to a light, you're braking. Instead of turning that into heat, you're using that energy to charge the supercapacitor. And then when it turns green, you can use that energy to accelerate. Okay. So that and your power from the battery, so you can, accelerate faster. So short-term energy storage from regenerative braking. That's what that means when you're not converting, when you're braking, you're not converting it into heat, but you're using it to charge the capacitors. Okay. All right, so let me, again, we are learning various things to reduce our carbon footprint. Okay. The global transportation carbon footprint is 23%. Okay. So we learned about a technology to reduce this carbon footprint. Okay, in 100 years from now, what are you hoping for? You're hoping that the world has a zero carbon footprint, essentially. Okay. So we've dumped a whole bunch of carbon dioxide in the atmosphere in the last 50 years. Okay. And if we can get to a zero carbon footprint before the temperature has risen too high, so within a couple of 100 years, the world will have changed. Okay. And that's the goal. What is the current global temperature? Well, let's start off. What was it in the 1800s? 14 degrees Celsius. What is it today? 15.2. We hope like hell it doesn't go about 15.5, but that's probably going to happen. What do we want? To be definitely below 16. Okay. All right, guys, I'm going to enjoy my donut now. Happy Thanksgiving.
Thanks.